Hello, I'm Kyle Long with Kinsey Ag Services, and today we're going to talk a little bit about soil. First of all, what is soil? Soil is rock and mineral that have been broken down over a period of time. But you may be asking, wait, Kyle, that just sounds like dirt. So what's the big deal? Well, dirt is dead. Now, I know that sounds morbid, but what I mean by that is that the soil is an ecosystem. It houses life in it and is full of minerals, nutrients, and living organisms. These organisms are the backbone of this ecosystem and what turn these broken rocks from dirt to soil. Microbiology plays a critical role in that it is what converts the nutrients that we put into the soil into a plant-usable form that the plant roots can take up. So, what makes a soil? Minerals are the primary particles that most people think of when they hear the words soil. These minerals are divided into three classes based on size: sand, silt, and clay. Sand being the largest particle, and clay being the smallest. The percentage of these different particles within a soil profile is known as the soil texture. In a primarily sandy soil, you generally feel a gritty feeling between your fingers as you rub the soil in between them. In a more silty soil, it feels more floury than gritty. And in heavy clay soil, in moist conditions, you can manipulate that soil and it holds its shape, much like modeling clay, hence why it's used in pottery and sculpting. The sand particle is the largest of the three. In a largely sandy soil, the particles are so big that they do not retain much water or nutrients, because the pore space is so large that whatever is introduced just falls into the profile quickly. Now, to demonstrate the differences in size in the sand, silt, and clay, I have here a container. Let's call this a section of soil. And then here is what we will call a sand particle. And what I want to do is I'm going to pour this water, and I'll do this for each of the mineral particles. And as soon as we start to get some accumulation down here is when I'll stop. So what I'm going to do is pour it right down the center. There's so much air in between these particles that as water is introduced, it quickly leaches down farther and farther, rather quickly, into that soil profile. Silt is the middle child of the three. It is smaller than sand, but larger than clay. It has trouble helping the soil retain water and nutrients as well, but the smaller size means that it does take longer for that leaching or draining into the subsoil to occur. So now what I'm going to do is I have here the sand particle that was used in the first demonstration, and now we're going to be using a silt particle. As you can see, quite a bit smaller than the sand particle. So we'll be filling our soil profile up with silt particles now. Let's see how long it takes for the water to leach down into the bottom here. Now it still fell rather quickly, but these particles are smaller than the sand. So there is less airspace between each of these particles. So as the water travels through, it is getting retained more effectively than what the sand particles could do. It's got a higher surface area, and so it takes longer for the water to actually drain into the bottom of these particles. Clay is the smallest mineral particle, and the best of the three to retain water and nutrients. Clay is special, though, in that it's the only particle of the three that actually can attract and hold nutrients to it. Clay minerals have a special property in that it has layers of unbonded oxygen atoms on its surface, allowing for positively charged ions, or cations, to able to be loosely attracted to that clay particle. This allows water and nutrients to actually be able to stay around longer and to be retained more effectively in that higher soil profile. Now here is our clay particle. Now if you remember, we had the sand particle, the silt particle, And now we have the clay particle, the smallest of the three. So now we will introduce the water to the clay. Took much longer to finally get down to the bottom of this container. Now, these are not scientifically accurate sizing differences in sand, silt, clay particles, but this was just to show you that as the particle size decreases, you get more retention in your water. So, of the three particles, clay has the most ability to retain nutrients and water faster. So, this was just a demonstration to show you all the different effects that each of the different particles has on retention. Organic matter is extremely important because it is the main food source of the biology in the soil. What makes up organic matter is dead and deteriorating plant and animal tissue in the soil, producing a food source known as carbon. This carbon and the other nutrients are what feed the microbiology and allow them to live and thrive. The top 2 inches of soil houses what we would call the organic layer, or the layer where most of the plant and animal residue is breaking down. This is because that dead plant material is sitting on top of the soil and decomposing, leading to bacteria, fungi, and other forms of soil life to go toward the top to feed from this buffet that was presented to them. Because of this, that's where the plant's primary feeder roots like to be, because it has the greatest population of beneficial workers to be able to convert and trade nutrients with. Another cool thing about organic matter, or humus as it's known after being fully broken down, is that after it's converted to humus, it, like clay particles, has an attractive effect on nutrients, and even thought to have more of an attraction to nutrients than clay, up to 3 times the attractive quality. It has been thought that this even allows for negatively charged ions, or anions, to be held in suspension longer when present in that organic layer. This is why broadcasting fertilizers on top of the soil is so important, because there are certain relationships that need to happen so that we gain the most effectiveness from our fertilizers. I have already briefly covered microbiology and living organisms, but basically there are 2 main types of organisms, aerobic and anaerobic. Aerobic soil life are organisms that need oxygen to live and thrive. Anaerobic soil life is life in the soil that does not need oxygen for respiration or to make energy. Most of your beneficial soil life lives in the aerobic areas of the soil, which is as deep as a fence post would rot. This area is generally 6 to 7 inches below the surface. Anything below this starts to go into anaerobic conditions. There is a transition layer between the aerobic and anaerobic conditions that goes from about 7 inches down to about a foot, with air restriction increasing as you go lower into the soil profile. The main microbial populations you find are the bacteria, fungi, algae, protozoa, nematodes, earthworms, and insects. What a mouthful. Each one of these has a different role in the soil, and while most can be beneficial to soil health, there are some that are predatory and not helpful. One cool thing is that you can actually physically interact with a certain bacterium present in the soil. Actinomycetes are a bacterium that gives off a distinct soil smell. If you have ever grabbed a handful of healthy soil and gave it a smell, you definitely have encountered that smell given off by these bacteria. They are mostly beneficial antibiotic that help keep your rhizosphere, or the zone around the plant roots, clean and free of predators. Another beneficial life form that you're probably familiar with is mycorrhiza. This is a fungus that is found in healthy soil. It is a fungal filament that attaches itself to plant roots and works symbiotically with the plant to help trade water and nutrients. This is especially important in helping the plant take in phosphorus, which is difficult for a plant root to do on its own. The plant, in return, gifts the mycorrhiza with carbohydrates that are developed from photosynthesis. Plants and animals need air to survive. Plant roots in biology are no different. Without air, we cannot expect to grow quality crops or have an ideal environment for the plant roots or soil biology. Air is only available with adequate pore space, which air needs to be half, and water being the other half of the pore space. Anything that begins to plug up or block pore space leads to restricted air in the soil profile, which will no doubt cause you issues. Too much air, however, is just as much of an issue. If we have too large of a pore space, then that means water and nutrients have more space to leach down further into the soil profile faster than what the plant or the biology can take up. Air is the byproduct of porosity. You can't introduce air to the soil. It occurs naturally based on the soil composition. The only way to manipulate the composition and to change porosity is by balancing certain cations that influence the soil structure, namely calcium and magnesium. But we'll get to that later. Water is probably the most important part of a soil's composition, alongside air. Water is the vehicle that drives the nutrients down into the soil and into the plant. Water is also where all these nutrient interactions can take place, in the medium where all chemical reactions are conducted. Without water, we would not have life.